introduce Dr. Zhe Jia. He comes to us from the Scripps Institution of Oceanography. Zhe got his master's degree at USTC and then went to Caltech for his PhD, where he graduated in 2022. And he then moved to Scripps, where he's now the Green's postdoctoral scholar, which is where he's sitting in my former office, so to speak. It's a great office. So Dr. Zhe has already worked on a wide range of problems in geophysics, broadly speaking, with focus on the earthquake source. And he has a number of different exciting perspectives on the related problems. And today he's going to talk to us on unraveling earthquake source complexities, implications for earthquake physics and hazard mitigation.
Thank you, Thorsten. Could you hear me clearly? Okay, great. Thank you all for coming to my seminar. I'm Zhe, an earthquake seismologist. So when my friend or somebody else know I'm an earthquake seismologist, the question they will ask me is, can we predict earthquake? And where will be the next big one? So these are the big questions, and I can only provide political answers, such as we don't really know, and there are limited understanding of the earthquake cycles, but I actually never lose the hope. And in this talk, I want to provide you with some of my thoughts about how complex earthquake sources are and what are the obstacles and challenges we need to overcome before we can really move forward. So let's start with some basic concept, and I believe many of you know plate tectonics very well, but I still want to emphasize that the Earth's shallowest layer is brittle and stiff, but they are separated into pieces named tectonic plates. These plates are moving like jigsaw puzzles around each other, and when they are moving, they rub each other at the interface, which cause earthquakes. If we look at the distribution of the earthquakes globally, as indicated by the colored circles, we can see that they correspond very well with the plate boundaries. So at least we have some sense where the major earthquakes are going to occur. However, the earthquake is still causing big problem and keeps threatening the society. This figure shows devastating earthquakes since 2000, and we can see that many of them caused hundreds to thousands of casualties. In the last year only, we see earthquakes at Turkey, Syria, Morocco, and Afghanistan caused tens of thousands of casualties. Many more got injured and huge economic losses. The society presently needs the scientific community to come up with better understanding of earthquake sources and a better mitigation strategy of the earthquake hazard. So where are we right now? Through the tens of years development in seismology and geophysics, we're able to do a lot of things. We can now do probabilistic seismic hazard assessment with a paleoseismological investigation of historical large earthquakes and the long-term deformation rate at a region. We can monitor the earthquake activity at a global scale very rapidly and down to a small magnitude. We can also do early warning with somewhat acceptable accuracy at some places in the world, such as California, Japan, and some places in China. However, there are a lot of things we cannot do. We cannot certainly prevent earthquakes. We cannot predict specific earthquake. We cannot reliably identify precursors, and we can't forecast earthquake characteristics. So what are stopping us from doing these things? If we think about the fundamental physical model of an earthquake, it's basically a sudden shear of rock along the fault. So the tectonic plate motion is constantly loading the stress along the fault. And when the stress accumulates and exceeds the frictional resistance, the sliding will occur. That's basically corresponding to earthquake's occurrence, and the strain energy being released, everything starts over again. If we think that the plate is moving in a relatively constant rate, and also our understanding of the frictional coefficient is in a reasonably good range, then what we should expect is that the stress accumulation and the earthquake occurrence should be relatively periodic. We should see earthquake cycles. However, in the real world, the earthquake occurrence is very complex. Here shows the major earthquakes in the past 2,000 years in San Andreas. We see many zigzags, and these lines indicated earthquakes with very irregular occurrence time and magnitude. So the key point is that the earthquakes are very different from each other, and we really need to understand their complexity behind. Through the rapid advancements in the instrumentation of seismic and geodetic stations at the global wide, we are able to see earthquakes more and more clearly, and we are increasingly surprised by how complex they are. Well, I can talk with you individually about how these earthquakes are complex, but it will take certainly much more time. So here I will emphasize on 3 examples: the 2019 Ridgecrest earthquake sequence at the crustal shear zone, the 2021 South Sandwich Island earthquake at the subduction interface, and the 2023 Turkey earthquakes at the continental strike slip boundary. So let's first go with the South Sandwich Island event. This event occurred at the southernmost portion of the Atlantic plate, which is subducting beneath the smaller South Sandwich plate. So at the subduction interface, when it breaks, a megathrust earthquake occurs, such like this event. When it happened, the USGS reported a magnitude 7.5, and what we expect for the tsunami hazard of a magnitude 7.5 event at a similar hypocentral depth would be like this. So the impact is regional, and considering the South Sandwich region is remote from coastal areas, we shouldn't concern too much about the tsunami hazard. But 1 day later, tide gauges at 3 major oceans at a distance up to 15,000 kilometers recorded a noticeable tsunami height of over 20 centimeters. And this basically means that the tsunami is a global spreading tsunami. The impact is huge. So what are we missing? Later, USGS reported there's another magnitude 8.1 that happened only 3 minutes after the first event, but it's reported 1 day later. We basically missed the opportunity to timely warn a global tsunami. So what causes this? This is because our current scheme in earthquake characterization and the tsunami response have blind spots. The first is that the waveform interference really limited the event identification. If we look at the seismograms here, the signal before the first event is very silent. So basically, we can identify the first event E1 very clearly. However, the first event generates a long seismic wave train, which covers the onset of the second event. This is the reason why it took USGS 1 day to determine its existence. The second reason is that we don't really know the SLAP model very well, and we don't know where the plate interfaces are. Also, the typical source inversion usually assume a smooth rupture on the planar fault, but there's a big curvature for the South American plate being subducted. So this limits our source inversion. To overcome these difficulties, I have developed a sub-event inversion method, which can fix these blind spots. The major advantage is that they can uncover unknown ruptures on unknown faults. The idea is simple. We decompose a complex earthquake into a series of simpler sub-events with different locations, times, and focal mechanisms. And this simple yet flexible parameterization really allow us to represent a broad range of rupture complexities of earthquake, including multi-fault and multi-episode rupture. So basically, we applied the inversion, and we found that the South Sandwich Island earthquake consists not 1, not 2, but 5 sub-events. The first event occurred at a deeper depth and have a magnitude 7.2. The second event rapidly transitioned to shallower depths and also have a similar magnitude. The third event is a special one. It propagated towards the south for 200 kilometers, and it has a magnitude 8.16. So this event itself is sufficient to generate a global spreading tsunami. The fourth and fifth event has a magnitude 7.6 and 7.7, and they're located about 300 kilometers to the south from the northern tip of this sequence. So basically, we found a special event E3 with a large magnitude. And another important characteristic is that the rupture velocity is very slow. It's only 1 kilometer per second, 3 times slower than the regular earthquake ruptures. So what does this slow rupture velocity mean to us and to the tsunami? If we take a look at the moment rate function, we can see that the third event consumes over 70% of the seismic moment and the strain energy. However, it is very silent at the regular periods we are looking at. These 3 rows shows the observed seismograms, the contributions from the other 4 sub-event, and the contribution from event E3. We can see that at the regular periods, the E3 is almost purely silent, and it's very difficult for us to identify its existence. Only at very long period, it starts to show up and pop up its potential to generate the tsunami. So this earthquake is an example that the complexity in the rupture episode really challenges our capability for the tsunami warning and responses. We're very lucky this time because the region is remote and the tsunami did not really hurt people, but we don't want to see this again. For the subduction interface, we know that the stress is accumulating and eventually there will be large earthquakes occurring there. But some crustal earthquake can provide with huge surprises as we don't even know the faults are there. A good example is the magnitude 6.4 and 7.1 Ridgecrest earthquake in 2019. The magnitude 7.1 is the largest California earthquake in the past 20 years. The Ridgecrest sequence occurred at the East California shear zone, which is a subparallel shear zone compared with the San Andreas fault. But it also accounts for 25% of the relative motion between the Pacific plate and North American plate. So after this earthquake sequence occurred, we responded very rapidly. And my collaborator, Zachary Ross, detected a lot of small earthquakes and relocated them. And after that, we found stunning orthogonal interlocked seismicity patterns as indicated by these colored dots in this map. So are there faults? And how are they ruptured by the main shocks? So we need to keep in mind that the Ridgecrest region is not large, it's actually quite compact. The total length of the scale is only 40 kilometers. So to actually be able to reach the fault mapping resolution when we are looking for the ruptures, we need new lenses. Only seismic data is not sufficient because it provides good temporal but not very good spatial resolution. So here I'm able to combine the seismic with INSAR and high-rate GPS data. From the modeling perspective, I developed a sub-event guided multi-fault slip inversion that we can flexibly adjust the fault geometry to test which one predict the data best. From the structural perspective, this region has a very strong 3D heterogeneity. As we can see, here's the China Lake Basin, which is very close to the fault zone. So we use a 3D velocity model to calculate the Green's functions instead of the regular 1D layered cake model we usually use. With these advancements, we are really able to see the detailed ruptures and the fault segments. So we found that the first magnitude 6.4 earthquake ruptured at least 2 orthogonal faults. With a single fault, we cannot predict the waveforms of the local and global seismic and high-rate GPS, as we can see this significant large misfits. Only with orthogonal faults, we can predict the data well. And this really shows that the data provide good constraints on the fault segments. So the second magnitude 7.1 is even more intriguing as the fault system inferred from the surface rupture and aftershocks cannot predict the seismic and INSAR data well. We see the significant misfits here and also the large chunk of blue and yellow misfits of the INSAR line of sight displacement. Only with the flower geometry, that is, there are 2 branches in the shallow portion, but they are connected with a deeper through-going fault. can we predict the seismograms and the INSAR data really well. So this means that we found a flower fault structure in which there are multiple shallow strands driven altogether by a deep through-going fault. So this stunning orthogonal faults and the flower fault structure really highlights the additional challenge brought by the complexity in the fault system, as the faults can potentially interact with each other, which compound the maximum magnitude and destructive potential. When we finished the research on the Ridgecrest earthquake sequence, this is an interpretation of the compounded damage. However, this turns to reality when the two big earthquakes occurred last year at Turkey. Turkey is a country with a long history of recording large devastating earthquakes, as there are two major plate boundaries in this country, the North Anatolian Fault and the East Anatolian Fault. These plate boundaries actually separate three plates, the Arabian, Eurasia, and Anatolian plate. The Arabian plate is moving constantly towards the north and compress the Eurasia plate. During this process, they're squeezing the Anatolian block to move towards the west. It's like we use the hand to squeeze a softball, and there will be a tendency for the ball to move out. And when the ball slips out, there will be a dislocation between our thumb and the ball. That's where the Turkey earthquakes occurred. So the biggest myth about the Turkey earthquakes is that why they're so large. If we take a look at the historical events as indicated by the colored segments over here along the East Anatolian Fault, we see that they are well separated by the kinks and stepovers, and they all have a magnitude around 7. However, this time, the first event unexpectedly ruptured through multiple segments and formed a magnitude 7.8 earthquake. The second event is even more surprising, as it ruptured the branch fault, Sugu fault, which is very silent in the past hundreds of years. So this larger than expected magnitude certainly contributed to the larger destructive potential. And one reflection is a 300-kilometer scar generated to the Earth's surface, equivalent to the distance from Austin to Dallas. So to really understand the physics and controlling processes of this earthquake sequence, we need to combine wisdom from geodesy, seismology, and the earthquake dynamics. So here we first use the geodetic data to constrain the complex fault geometry. We found that this earthquake sequence involved at least 6 major faults and over 10 fault segments, very complex fault geometry. This fault system in front shows the magnitude 7.8. The system to the back shows magnitude 7.7. Although they are very close, they are not connected with each other. So with this understanding of the geometry, we are able to investigate the next question: how the ruptures developed and evolved with time and space. So I was able to combine the geodetic data and seismic data and conduct joint inversions to constrain the complex rupture processes. As I'm going to play the video, you will be able to see how the rupture indicated by the color migrates along the fault system. The first 7.8 earthquake initiated on the branch fault, but then it quickly transitioned to the East Anatolian Fault and was able to overcome a series of geometric barriers, including junctions and kinks, like a car rushing through these stop signs and propagated for 300 kilometers. Moreover, when it arrived the East Anatolian Fault, it first ruptured towards the northeast, and then there was a delayed backward branching, which is very rarely observed for large earthquakes, and it is considered to be mechanically unfavored. The second magnitude 7.7 initiated on the central branch of the fault system and ruptured bilaterally, but the westward rupture is much faster. Turns out it has a super shear rupture episode. So the super shear rupture is like a sonic boom when an aircraft exceeds the sound wave speed, and then we know the sonic boom is very loud. This is also what super shear rupture brings us, a very strong energy carried by the seismic waves and the stronger destructive potential. So now we have a good understanding of the kinematic rupture processes, and we want to know what controls these evolutions. So we conducted dynamic simulations to replicate what we have seen from the data using a realistic fault geometry and a relatively reasonable and simple assumption of the pre-stress and strength distribution along the fault system. So we're able to recover the most features we see from the observations and discovered a series of very interesting stress-mediated phenomena, including unclamping, transient stressing, and pre-stress heterogeneities. So for example, the delayed backward branching during the first earthquake is caused by the dynamic unclamping effect. That is, the rupture propagated towards the forward branch will generate dynamic stress perturbations that gradually unclamp the backward branch. When the normal stress is reduced to a certain level, it allows the slip to occur and then opens a gate for the rupture propagation of another 150 kilometers. So for the second magnitude 7.7 earthquake, the regional principal stress orientations and the curved fault geometry really allow the existence of a pre-stress heterogeneity, which promoted the supershear rupture episode to occur. So this Turkey earthquake really shows that the fault segments can talk with each other, and it is their complex stress interactions that really made the rupture propagate one fault by one fault and eventually accumulated into a magnitude 8 earthquake sequence. So we have made a series of very interesting observations showing the remarkable earthquake rupture complexities, including the multi-episode, the multi-fault ruptures, and unexpected cascading. We see that this really compound the potential damages of earthquake and challenges our hazard mitigation and responses. But also I view them as special opportunities because this observation really allow us to think what controls these complexities. So to move forward, we need to investigate these potential controlling factors. The possible controlling factors include the fault geometry, temperature and pressure, stress, and other dynamic factors. There are many, but here I want to use two examples to show you how we investigate them. Let's first go with the fault geometry. We have shown that during the Ridgecrest earthquake, the crustal earthquake rupture really brought us surprise about the fault system. And is it possible for us to know the fault geometries without seeing a major earthquake rupture to the surface? The answer is yes. And what we are going to do is to illuminate the faults with small earthquake rupture directivities. This map, the circles in this map shows the magnitude 3.5 to 5.5 earthquakes, and we see it covers the region well. And the beautiful feature about rupture directivity is that one directivity shows one fault. We don't really need a lot of events, and we can see the fault system very well. So how do we constrain the directivity? It's like a car driving by us, and the sound we hear is different from the beginning to the end. It's a Doppler effect. And we also hear the Doppler effect from the seismograms at different stations. So here I developed a new method to determine the source time function and to constrain the rupture directivity. The basic idea is the empirical Green's function idea. The basic idea of that is we use an earthquake twin to cancel out the common path effect. And we also take advantage of the power of the envelope as the raw waveforms introduces aliasing and cycle skipping when we are doing deconvolution at high frequencies for small events. But the envelope retains the coherency across different stations. So here is a comparison between the conventional method and our new method. We see that our method really recovers the beautiful cosine-shaped Doppler effect, a Doppler-like curve, and recovered the true rupture directivity as input very well. So this is good. And we are able to obtain over 70 rupture directivities across the Ridgecrest fault system, as shown by these orange arrows on each moment tensors, on each beach balls. So this directivities really divide this fault region into 3 subregions, 1, 2, 3. And if we go across them one by one, the first region shows very complex fault geometries, multi-faults oriented different way and cutting across each other. There are complex antithetic and split faults. The second region is rather simple. There is a through-going fault that was cut across by one or two fault branches. The third region is also very complex. There are multiple horsetails and multiple splay faults cutting across, forming a splay and subsidiary fault system. So basically, we have one simple region sandwiched by two complex regions. So what does it mean for us? If we quantify the geometric complexity in this map as red shows simpler fault, we found there's a good coherence between this and the stress drop distribution estimated independently. It corresponds to higher stress drop at the middle segment. So a possible explanation is that when the fault is very complex, there are more geometric barriers such as junctions and kinks, which stop the rupture to develop to higher slip and higher stress drop. However, when the fault is smooth, it allows the rupture to develop and the stress drop will be higher. This is also consistent with the fact that the magnitude 7.1 main shock has the largest slip and the stress drop in the central segment. So this example really shows that if we know a regional fault geometry very well, we can potentially anticipate some aspect of the earthquake characteristics. Another factor is the temperature and pressure. We know that the temperature and pressure really goes up rapidly as the depth goes deeper, and we want to explore the extreme cases in the Earth. So this really brings us to the deep earthquake that can occur between a depth range between 500 kilometers and 700 kilometers. For a long time in the history of seismology, deep earthquake has been the most important slab illuminator, as they provide important constraints and evidence on the slab shape, the stress environment, and the dynamics. However, the temperature and pressure should be so high that prohibit any brittle failure. Then why deep earthquake can occur? There have been several mechanisms being hypothesized, such as the transformational faulting of the metastable olivine wedge. That is, in the phase transformation to the Wasserlitz and ringwoodite, it will experience volume change and induce faulting. Another mechanism is called shear melting. That is, when the rupture already exists, it generates melt that can lubricate the fault and allow the rupture to further propagate. But no definitive mechanism have been confirmed yet, and we need to really compare the rupture processes and the slab environment in a global scale. So this sounds very ambitious, and how do we do this? I have developed the sub-event inversion method with a new linear framework, and it really allows a 10 times faster speed improvement compared with the previous nonlinear inversion scheme, while we are able to retain the most good features of the sub-event inversion. This really allows a systematic investigation of rupture processes on all 40 magnitude larger than 7 earthquakes since 1990. We also need to understand the slab environment. So we conducted the thermal simulation of the 7 subduction zones that can host large deep earthquake, and use a phase diagram to determine where the metastable olivine wedge should be. So this solid lines shows the inferred metastable olivine wedges, and we can see that they have very different structure across different slabs. So now we have these two components, and the comparison between their dimensions really shows that larger earthquakes can rupture outside of the metastable olivine wedge. This is an example of the 2013 magnitude 8.3 Okhotsk earthquake. This beach ball shows the initial and the ending sub-event, and we can see that its dimension cannot be accommodated by the metastable olivine wedge indicated by the blue chunk. Similar thing happens for the Tonga slab, that the 1994 and 2018 Fiji earthquakes initiated at the coldest core of the MOW, but eventually ruptured outside of it. If we systematically compare the cross-slab rupture length of these events and also the metastable olivine width, we see that over half of the large earthquakes should have ruptured outside of the metastable olivine wedge. This means that should encountered shear melting mechanism. Another very interesting observation we made is that we saw the focal mechanism can rotate during a single earthquake's rupture process. Here's an example of the 1994 Fiji earthquake. We see the first and the last sub-event have very different focal mechanisms, strike angle. This means that they cannot be accommodated by one single fault plane. The fault geometry must be very complex. If we quantify this geometric complexity with the focal mechanism rotation, as indicated by the color from yellow to dark red, we see that as the earthquake goes larger, the mechanism rotation also goes larger. Also, we see when the earthquake has a larger magnitude, the stress drop indicated by the y-axis increased by an order of magnitude, which is substantial. And this is also in a good agreement with independent study on independent data set, as shown by these blue circles and these triangles. These triangles are measurements made by Alice Turner, who is over here. So now the question is why there is a magnitude-dependent physical properties for large deep earthquakes. If we consider the fact that they can rupture out of the metastable Olivan wedge, we can actually make the interpretation that the slab environment was really able to gate the mechanism transition between two mechanisms and is able to control the deep earthquake characteristics. Smaller events tend to be confined in the metastable Olivan wedge, and they're mostly dominated by the transformational faulting mechanism, which typically show lower stress drop and less geometric complexity. While the larger event can extend beyond the boundary and transition its mechanism to shear melting, which turns to have higher stress drop, and this transition can introduce more geometric complexity. This very simple model is able to explain a diverse range of the deep earthquake behaviors that we made. This is a good example showing if we really understand the regional slab environment very well, we can potentially anticipate what the large deep earthquake will look like. So here I want to summarize the takeaways into 2 bullet points that we first was able to see the rupture complexities. We see them and we need to know that they can amplify the natural hazard and they can change conventional wisdom on the earthquake physics. When we see it, we also need to deal with it. We investigate the controlling factors, and this can help us to understand the earthquake physics better and possibly help us to anticipate future earthquakes behavior. So now what about the future? The future of earthquake source studies really lies in a vast range of large earthquakes occurred at the different tectonic regimes. Here shows a map of large earthquakes since 1990, and we can see that there are over 500 magnitude larger than 7 events, but only a very small portion of them have been carefully studied. They actually contain rich information about the rupture complexities and what are the controlling factors across different tectonic regimes. With the exploding data and instrumentation, as well as the evolving supercomputing power, I intend to systematically investigate the rupture complexities of these events, both from data-oriented and physics-based perspective. I have shown that systematic analysis is technically feasible, and this will bring us new understandings of earthquake physics. So studying earthquake is also very important for us to understand the Earth's structure and dynamics as these 2 components are tangled with each other. For example, as we show in the South Sandwich Island earthquake, there is a distinct slow rupture episode in the middle. And this is potentially induced by the difference in the fluid penetration into the subduction interface along different segments of the strike. And also, another factor is the variation of the upper plate rigidity, because the slab has a strong curvature and the age at different segments of the upper plate is very different. The other example is that some deeper intra-slab earthquake can really reflect the slab interactions, such as the 2018 Fiji Tonga earthquakes really shows how a remnant slab is detached, sinks, and leans on the Tonga slab. This is a good reflector of slab bending and collisions. So to sum up, to do a short summary, there are important questions we can address, which include how do earthquakes interact with slab structure and dynamics, how fault conditions vary along strike and deep, and also what role does stress and fluids play. We have many exciting places in the world that wait for us to investigate, such as Hikurangi and Alaska subduction zones, and the New Zealand and California shear zones, and many other places in the world. And studying these regions on the earthquake sources and the subduction interfaces or the fault zones really match very well with the NSF Earth Science priorities, 3 of 12, I think. So also, we need to come up with new hazard mitigation strategies. And a particular challenge is that how can we better warn earthquake and tsunamis before they really start to hurt people? So what I will do is to develop the next generation earthquake source characterizations to help the tsunami and earthquake warning and responses. An example is what we have done for the South Sandwich Island earthquake, and we see the potential that it can improve our current tsunami warning strategies. Also, the other question is, when the earthquake happens, where will be the largest shaking? And here it shows a wave field simulation when the large earthquake occurred at Southern California, and we see it's different from our expectation that the largest shaking actually occurred in the poor Los Angeles basin. I lived in Los Angeles for quite a few years, and I know it is a big risk. And what I will do is to use the new densaries, including nodes and DAS, to empower our structural imaging and ground motion predictions. Here shows an illustration that I used 16,000 nodal sensors and broadband stations to provide a high-resolution image of the Los Angeles basin structure with high fidelity. So for these hazard-related projects, they are very tightly associated with the interest of multiple agencies, including USGS, SCAG, and Crescent, and I will actively apply for funding from them. So here I want to spend some time to talk about my career goal. My career goal is really to form new understanding of earthquake physics and to open the door for practical earthquake forecasting. And it's like solving earthquake puzzle. We really need a very good understanding of earthquake physics, but we also need other components, including the stress and strength of the faults, the fault structure and geometry, and the dynamic factors such as fluid and heat, and many others. So this jigsaw puzzle can be addressed through advanced rupture imaging, high-resolution fault mapping, 4D spatial temporal moment tensors and stress inversions, and multidisciplinary earthquake simulators, both from experiment and numerical perspective. So with these progresses, all of the components are addressable, and I believe in the next 10 years, we will be able to see the major advancements in these components. So let's go back to the very first slide, what we can, what we can't. There are still a lot of challenges, but we are in the era that we are building the next generation earthquake source and the earth structural models, and connecting the empirical and physical understanding of earthquakes. So eventually we are getting better and better understanding of earthquake source characteristics. And if we understand it very well, there may be a hope to move the forecasting of earthquake characteristics practical. This may also open the door for something more and more exciting. So here I would like to thank my collaborators and thank you all for listening. Please feel free to ask any question you want.
Thanks a lot for the presentation. We have plenty of time for questions. I'll start out with one. So we know that, so this sort of fault linking up stuff, right? It seems like the Eastern California shear zone has been telling us a story there for a while, starting with Landers. And after Landers, 3 map faults connecting, people started to really do a lot of work on sort of fault rupture jumping probabilities. So I wonder, when you then look at what happened basically in any of the cases you analyzed, what's the sort of new component? So I understand there's like this dynamically delayed effect you were invoking for setting things off. So is that something that had not been considered as much by earlier jumping studies, for example?
Well, this is actually a very interesting point, because I think in the Landers like 1992, people have also observed about the backward branching, although it's a much smaller branch. I think the phenomena itself is not 100% fresh, but it's about how we understand it, how we view it, what's the potential, and what does this means to the hazard assessment. For example, the Turkey earthquake really shows that if we do not consider the potential of the rupture jumping through the forward branch to the backward branch, we can really underestimate the largest magnitude and the rupture extent of that. And it's also somewhat similar to what we see in California, because before the Ridgecrest earthquake, I think many people consider the earthquake hazard at Southern California based on the large historical events, like the magnitude 8 at 1858, right? But it really shows that multiple faults can rupture in one earthquake. And it's important because the Ridgecrest earthquake stopped about only several kilometers away from the Gallup fault. We are fortunate this time, but we don't know if it had ruptured the Gallup fault. Should it involve another magnitude 8 earthquake, we could be very close to that. So the point is, we really need to assess the possible rupture scenarios as best as we can, and we need to consider the fault interactions in a as complete sense as we can get.
A question online from Peter Eichhobel.
Yeah, thank you. So very clear and good presentation. I really would like to comment on this. My question for you is, if you could comment on the significance of poor elastic strain and stress transfer, especially for crustal earthquakes. There's obviously a history of talking about fluid diffusion for earthquake dynamics, and for induced seismicity, we have been able to demonstrate how significant poor elastic strains and stress transfer is. But I'm not sure if this has received much attention in the recent natural earthquake community. I wonder if you could comment on that. You mentioned fluids a little bit, but it's getting more complex when you talk about poor elasticity, right?
Thank you, Peter. So this is a very important topic, the fluid. I haven't mentioned it much, but certainly it can potentially impact a lot of rupture complexities. And this is certainly one direction I'm going to go in the future. So certainly we all know that fluid can increase the pole pressure, decrease the normal stress, and impact the frictional behavior along the fault. The thing that people have paid less attention about, here I want to actually use the Turkey earthquake as an example, is that the fluid can also potentially modulate time-dependent rupture behaviors. So for example, the first magnitude 7.8 earthquake ruptured, and 9 hours later, it triggered the second magnitude 7.7. So currently, we have a good understanding of these two earthquakes' individual rupture processes, but I think we haven't reached a very good story about how the first event triggered the second one. We have calculated the static and dynamic stress perturbations, and we show that indeed the first event posed a positive stressing at the location of the second earthquake's occurrence. But why there was a 9-hour delay? And this delay, and one explanation is certainly related to fluid. The dynamic stress perturbation may be able to open some tunnels for the fluid and cause fluid upwelling. And if this is time dependent, it may gradually increase the pole pressure and eventually unlock the fault, allow the rupture to occur. But this really requires combination of co-seismic and interseismic studies, and also the study of the fault zone structure itself. We need to understand where the fluid exists and what's the existing pull pressure of the fault system. So another example, as I mentioned before, is the South Sandwich Island earthquake. Let me find it. As we see that there is a distinct episode. This is, in my opinion, very possibly related to fluid intrusion into the slab interface, as for subduction zone earthquake, it's really, we need to really think carefully about what modulates the rupture velocity change from one segment to the other. So the fluid may be carried into the fault interface through multiple ways, like the sediment, may potentially upcrust, but I think Floto yesterday mentioned that the outright fault is not a very efficient way to carry fluid into the shallow megathrust. But the point is that the fluid itself is able to change the slip behaviors, not by promoting rupture, but also sometimes by stopping the rupture to be fast. It's like a competing mechanism, including the pull pressure, but also decrease the potential of fast and rapid ruptures. So we certainly need more study and to combine the different scopes altogether.
Questions, Alice?
Hi, thank you so much for a really great talk. I just wanted to ask you, so you mentioned that you've developed this sub-event methodology. Can you expand a little bit on how it's new and different to other people who have used this sub-event method before?
Yeah, thank you. Sub-event idea is not proposed by me. Actually, it's proposed by Kikuchi and Kanamori up to, I think, 1990s. So at that time, the idea is that when we study earthquakes, we need to discretize a fault into small grids. And then they think, oh, why not using moment tensors to describe them? And then they just conduct this parameterization and deconvolve the seismograms one by one. That is, first use one sub-event to describe the waveform, and then subtract the contribution of this sub-event, and then determine the next one, and do this iteratively. However, this certainly has its advantage as it's fast and efficient, but there are limitations. It's hard for us to really distinguish the contribution to the seismograms at different location and different time. So what we're doing here is ideally similar, but practically very different. We simultaneously invert for all sub-events altogether with a search of their locations, times, and focal mechanism. And this search is through a multiple Monte Carlo Markov Monte Carlo inversion, multiple chain Markov Monte Carlo inversion. It's complicated, but the point is that we generate a lot of chains, and each chain consists tens of thousands of samples, and we do this search through the random walk. We try to investigate the parameter space as complete as we can. So this way, we get a good understanding not only about the optimal model, but also the uncertainties as we have the ensemble, right? And we are confident that the exploration of the parameter space is much better.
And just a quick question. So do you predefine the number of sub-events that you have, or is that a free parameter in your inversion as well?
That's a very good question. So here, we iteratively add the number of sub-events in each inversion. We start from a small number, like 2, and then add 1 and do inversion, add 1 and do inversion, until the fit to the data reaches the level that we think it predicts most of the important features in the seismogram. It's like when we are doing the tomography, we have the error curve, right, between the model complexity and the misfit. So we basically want to find a corner that we fit the data very well, but we do not want too many unknown parameters. One way to illustrate this is that here in the backup slides, I have some waveforms for you to see. Yeah, here is the, if you look at the right side waveforms, this only shows a small portion of that. This shows that we need first two sub-event to fit the first initial wiggles in the seismogram. We need the third sub-event to fit a large component of the original very long period waves, and we need the last two sub-event to fit the later signals in the body waves. So basically, we are looking at these key features in our inversion. Yeah, and in the future, to make it even more automatic, I will possibly introduce the transdimensional Markov chain Monte Carlo inversion to make the algorithm be able to determine the dimension automatically.
Thank you very much.
Thank you.
Luke.
Try and throw it.
Thanks.
Incomplete.
Thorsten. So I have a question about the deep earthquakes.
Sure.
You know, are you confident? Are you very confident in the temperature structure of the slabs when you put the?
Yeah, that's a very good question because yeah, I discussed extensively with my collaborator Wimo, who is a postdoc of Mike Gurnis, and when I was at during my PhD, I also discussed a lot with Mike on this. So the point is that we don't really know a lot about the slab temperature and structural profile. And what we are trying to do here is to make the framework as simple as possible while introduce other constraints to calibrate it. So here we did not do dynamic simulations. Instead, we use reasonable slab geometry, the slab convergence rate, and the slab age to solve the diffusion problem and to do the thermal simulation. And then we calibrate the absolute temperature at the depth of 240 kilometers with, I think it's a Syracuse paper, Syracuse and yeah, it's a Syracuse paper in 2010. That is the fully dynamic model. So basically, they have accounted for a lot of factors and generated a reasonably good range of the absolute temperature. And we try to calibrate that. We also tried to account for some factors about the uncertainty of these thermal simulations, such as what's the adiabatic temperature profile will look like and what's the possible range. And we found that the lower bound is better constrained than the upper bound of the temperature. It can be much warmer, but it cannot be much colder. Mm-hmm. So in terms of the implication on the MOW, it will likely only make the MOW to be even thinner. So it doesn't impact much about our conclusion that the earthquake can rupture beyond the MOW, because if it's warmer, then it can rupture even more.
Very lucky.
Yeah, that's very lucky.
Yeah, so also I have a question about the Turkey earthquake. So yeah, it's with your method, could you kind of predict or not predict, but forecast whether or not you could break through everything, because you seem like to be able to jump from one to another. So could you do some sort of a model where an inversion where you could break through the whole length of the fault zones?
Yeah, that's a very good question. So certainly with some tuning of the pre-stress, we can make all of things happening all together. But note that the prescribed stress and stress distribution along the fault should follow some, we should have some reasons to do that, right? Yeah, we need to combine the understanding from the regional moment tensors, the long-term strain rate and the principal stress axis, and also our understanding of other large earthquakes stress and strength ratios to give that. So this really make us to be able to not instantly nucleate the second earthquake. This is very interesting. The first earthquake and the second earthquake, although their fault systems are connected with each other, the first event did not trigger the second event instantly. So this is an example how the stress really mediates the rupture occurrence, but also limits its extent. Yeah.
So I guess I have a follow-up in exactly in this area. So can you quantify what the amount of dynamic unclamping is and whether or not, or make an attempt anyway,
Yeah,
whether
yeah,
or not the backward rupture would or would not happen?
yeah. This is a very good point. I think we certainly are on the track of trying to better quantify these scenarios. And over in this case, actually, the unclamping effect is quite clear and it's quite robust also. I think it's very much related to the geometry as the geometric settings, the angles between the subsidiary fault and the main East Anatolian fault. And the unclamping is able to make substantial contributions. And I think the scholars at UC Riverside also reached a similar conclusion. In the future, we are going to better quantify these things. And the difficulty is really part in that it's not easy to constrain the absolute stress and strength, right? In the fault system, they're coupled with each other. So what we are prescribing here is the stress ratio to the relative strength and relative stress. So translating understanding from the dynamic models to what the real stress amount, especially the absolute value, is a challenge, and we need to think about ways to overcome this. But it's certainly the way that we are going.
Right, Damien.
Yeah, so this is kind of a follow-up question, I guess, but I mean, do you have enough confidence in the rupture models to take this a step further and try to kind of hindcast the excess strength distribution, right, or the pre-stress distribution on a fault, or at least place bounds on that? Because I could imagine that even though that's not forecasting, you could then evaluate that in the context of the preceding ruptures, for example, and learn something about that ambient condition.
Yeah. This is a very good point. We should really need to think about what one earthquake what's one earthquake's impact on the stress field and how it changes the behavior of future earthquakes. We are indeed going to look at the earthquake dynamic stress perturbations, not only for one earthquake, but also during the cycles of different events. This is pretty important in the Turkey region, because along the East Anatolian fault in the history, there are quite a few examples that they rupture the segment by segment, but eventually this time they rupture all the whole. If we think about what causes the pre-stress heterogeneity, it's very likely due to the historical events, right? As I mentioned, constraining the absolute stress level is difficult, but at least this can potentially give us a sense of possible upper bound and lower bound. And we also need to simulate not one earthquake, but also multiple events that we can see in the cycle in the past at least hundreds of years. I think there are some ongoing studies by different groups, and certainly that's one very interesting topic that I want to look into.
All right, let's thank Dr. Zhe again.
Thank you.